Okay, so all right, let's. Oh, I totally forgot about view quiz, but whatever. Okay, so you guys have a midterm on Wednesday, so so you have that. So today, the stuff I cover today will not appear on Wednesday. Okay, and don't worry. And I thought we would take like a small detour this week, where we apply the Metropolis algorithm to in kind of maybe an interesting use case. I think it's kind of an interesting use case. Because so far, the Metropolis algorithm, like we've talked about how it works, but the application has been rather, in my opinion, lackluster. It's just kind of like, how can we run the Metropolis algorithm so we get a sample from the normal distribution? And it just seems very silly that we would run, in real life, you would never use the Metropolis algorithm to get a sample from the normal distribution, because we can generate the normal distribution in lots of other ways, right? We got our norm already built into the computer, but you have the Box-Mueller transform. You got all sorts of ways to deal with stuff like that, and so we wouldn't actually use the Metropolis algorithm in those cases. But there are situations where the Metropolis algorithm or the Metropolis Hastings algorithm is actually useful, or is probably the only practical approach towards the problem. Okay, and one example here, and we're going to look at one example here. Okay, now one very nice feature of the Metropolis algorithm is that you don't actually need to know the probability distribution. You only need a function that is proportional to the probability distribution, right? So this is a property of the Metropolis algorithm, is that in order to calculate kind of your probability of moving to a proposed state, you only need to know a function that is proportional to the target probability distribution. You don't actually need to know the target probability distribution itself. And that is useful, that property is useful when we are looking at, say, a Bayesian problem, okay? Because in a Bayesian problem, the marginal probability, which is a normalizing constant, that thing is often difficult to figure out. Okay? All right, so here's an example where we're going to run the Metropolis algorithm, and we run into this situation that I'm talking about where the exact probability is difficult, but finding a function where it's proportional is reasonable. Okay? So let's go ahead and take a look. Okay? So the idea here is we want to decode the text of a substitution cipher, okay? So I don't know if you guys ever did something like this, maybe in elementary school, where you'd have like a little puzzle, or maybe you would try to send your friend a secret message, okay? Where you had a substitution cipher, right? So across the top, I have the letters of the alphabet, A, B, C, D, E, F, G, all the way through X, Y, Z. And then you have a mapping, a letter mapping, okay? Where the letter A becomes the letter C. It gets substituted with the letter C, or the character C. The letter B gets substituted with the character D, and so on and so forth. And so if you wanted to send this secret message, hello friend, the H becomes a B, the E becomes a U, the L becomes an M, the two L's become an M, O becomes an I, F becomes J, and so on and so forth. N happens to be mapped to itself. That's just a coincidence. This is just a random mapping. And so the phrase, hello friend, becomes BUMMI JKFUNO, okay? and then your friend receives this, your friend would need to have this cipher key, and then they would say, okay, B goes back to H, U goes back to E, so on and so forth, and they would decode it, right? So, did you guys ever do something like this? Maybe there was like a little puzzle in an activity book or something like this, right? Okay, and so this is actually a real life problem where there were, I guess there were prison guards, there were people in prison, and they were sending messages like this to each other, and the prison guards intercepted the message, and it was just kind of gibberish, and they wanted to know what was the original message, and they were trying to figure this out. And they couldn't figure out what the messages were, so they went to a university professor, and they said, hey, can you help us out? And the solution was to apply the Metropolis algorithm to kind of get through the answers, okay? And so the question is, if we see a ciphered message like this, right? You see this scramble of characters, can we figure out the original message? Can we go from B-U-M-M-I, J-K-F-U-N-O to H-E-L-L-O-F-R-I-E-N-D, hello friend, and figure out the message? Okay? This is the problem that we're trying to solve, okay? So just to kind of set us up, okay, we're going to say, well, one thing we can do is we can just try a brute force approach, right? How many combinations would there be if we were to try a brute force approach? There would be 26 factorial, all right? So assuming space goes to space, and we're just scrambling up the 26 letters of the alphabet, there would be 26 factorial possibilities that you'd have to try out, okay, if you were going to do a brute force approach, right? And so 26 factorial, what is that? (26 exclamation point) is 4 times 10 to the 26. Okay, so coincidentally, so 10 to the 26, what is that? That's a trillion trillions, something like that, okay? It's a lot, okay? 4 to the 10 to the 26 is it's just too many, okay? So we can't, we don't want to have to try to do something like that, okay? So what we want to do is we want to kind of take a slightly smarter approach than just straight brute forcing, okay? And anyway, even if you were to brute force it, how would you know when you come to a solution, right? Because if you're just having the computer like zip through all of these, like when will the computer know to stop, okay? So anyway, let me just tell you, so let's say these are just two potential keys, right? So you say, okay, well, here's one random combination of letters. Here's another random combination of letters, okay? And so if we use this key, this first one, potential key 1, and we were to feed it through, put B-U-M-M-I, J-K-F-U-N-O into potential key 1, what would the translation be, okay? B goes to G, U goes to U, M goes to V, and I goes to W. So this becomes G-U-V-V-W, and then J-K-F-U-N-O becomes Y-Q-P-U-C-H, right? So this says if the original text, if the person creating the cipher message had used potential key 1, this was their original message, G-U-V-V-W, Y-Q-P-U-C-H, and after applying the substitution key, this is the text we got, B-U-M-M-I, J-K-F-U-N-O, right? And then here's another potential key, all right? Just another arbitrary arrangement of letters, and we say, okay, if the person had used this key, then the original text would have been this, R-A-L-L-P, C-H-O-A-M-X, and if they applied potential key this key to this original text, it would produce the text that we encountered, BUMMI, JKFUNO, okay? All right, now are either of these keys correct? Obviously not. Well, I mean, not obviously not. There is a very small but non-zero probability that this is the original text that they wanted to transmit, right? Maybe it was like, what was the license plate of the thing that you, right? And it could be just some gibberish thing, and this could be the original message, GUVVW, and therefore when they ciphered it, we ended up getting this, right? And there's also a very small but non-zero probability that this was the original message and this, right? But we're gonna kind of make the assumption that what they're trying to transmit looks like English, okay? That's gonna be kind of an assumption that we're gonna make, all right? And if we make the assumption that the original text should look like English, which one, potential key 1 or potential key 2, would you say looks more like English and therefore is the more likely key? The second one, right? What is it about the second one that makes it look more like, again, I don't think this is the original message, but it seems like this is closer to the original message than the first key, and why? What is it about it that you see?
I think the proportion of each characters.
So, I mean, yeah, we only have a few characters. Yeah, so we're looking at the proportion of the characters. Okay.
Familiar to what
And both of these have like these, you know, odd characters, the Q and the X. Like these don't pop up very often. But there's something about seeing the combination QP, right? Like how often do you see the letter Q followed by the letter P in English? Almost never, right? Very, very rarely in reading, right? Also, Y followed by Q. I don't know if that ever really happens in regular things, right? But, you know, C followed by H, I mean, that appears here also. This part is not weird, but this YQP seems very strange. This VVW seems very strange, right? Okay? Whereas ALL, RALL, that's like, oh, okay, that seems not weird at all. Okay, the LP, you know, it's a little bit weird. CHOA, like, these are not strange letter combinations. Okay? So there's something that tells us that this text looks more probable than this text. Okay? And so because this text seems more probable than this text, that makes potential key 2 more probable than potential key 1. Right? Does that kind of logic make sense? Because the potential text seems more probable than the other one, this potential key seems more probable than the other. Okay? And that's effectively Bayesian reasoning. Okay? That's effectively Bayesian reasoning. We're saying because the likelihood of the data is more likely than for this given parameter, then that makes this parameter more likely for the given data. Okay? So let me go ahead and give you your first view quiz answer for today. Today's first view quiz answer is the letter D. D as in dog. D as in dog. Okay. So what we have, what we're going to do is you just apply some Bayes rule, okay? And what we want to know is we want to figure out basically our posterior is what is the probability of a particular character mapping, okay? The character mapping, okay, given our data, which is the text BUMMI, whatever it was, JKFUNO, okay? Or what So given our data, which is this text message, we want to figure out what is the character mapping, okay? So using Bayes' rule, this is going to be the probability of our text, BUMMI, JKFUNO, okay, given the mapping, character mapping, times the prior probability. I'm going to move that out of the way, okay? So just of some particular character mapping divided by the probability of this text. Okay? And so the likelihood, which is basically the probability of the text, I'm going to just write probability of the text given the character mapping. Okay, is basically going to ask, what is the probability that we had some original message that produced the observed text. Okay, so basically probability of, what are my choices? GU, VV, W, YQ, PU, CH. Probability of RALP, R-A-L-L-P. And we're going to say, what was the probability? You know, this seems more probable as the original message. That's our likelihood. Okay. The prior is just the probability of some character mapping. Okay, and as far as this goes, prior to looking at the data, we have no reason to believe that a particular character mapping is more probable than any other particular character mapping, right? Prior to seeing any data, sorry, I'm running out of space here. Any particular mapping is more probable than another. Okay, so what that means is that we'll just use a constant. Okay, we'll just use the same constant for all the priors. Does that make sense? Because we're not going to say that this particular character mapping is more likely than another character mapping. So we're just going to use a constant for everybody. All character mappings equally likely. Okay, and then the marginal, would be basically the probability of the text, okay? And this is also another constant, and it's the sum of the numerator across all possible character mappings. Right? So when we did Bayesian stats, we said we got to figure out the numerator across all possible values of the parameter, the character mapping, okay? And there's just too many. There's 26 factorial character mappings to consider. We're not going to be able to figure this out. We're not going to be able to figure out this marginal probability, right? Calculating the marginal is too much work. 26 factorial mappings. Okay. We're not going to get this, okay? It's too many. Okay, but that's okay, because we have the Metropolis algorithm. The Metropolis algorithm says, you know what? The answer that we're looking for, hang on, 1 on 2C, I want to save this, week 7, week 6, Monday, let me put, this is 2021, week 6, no, week 7 Monday, slide 1, okay. 26 factorial possible mappings, we're not going to figure that out, okay? But what we have is the probability of the mapping, the character mapping, I should say, given the text, is what? Is proportional to the probability of the text given some character mapping times the probability of the character mapping. Okay? And we said this is a constant. Okay, so that just means what we're looking for, so our f of x is just going to be the probability of the text given the character mapping. Okay, so how do we figure out this? How do we evaluate the text? Right? How do we figure out this thing? Okay, so we ask, so with, and maybe I'll just copy this. So we're going to go, basically we want to know what is the probability that this was the original message. Okay, and we're going to ask the same question to this one. What is the probability that this was the original text? Okay. And so our intuition says RALLPCHOAMX is more likely to be the original text. It's not the original text, but it seems if we were forced a choice, this one seems a little bit more likely as the original text, okay? So that means potential key 2 is the more likely character mapping. Okay, so there's a few ways, okay? So our probability of the text, probability of some original message is going to be, we're going to use kind of two things, all right? We're going to use probability of the text So, and you can take different approaches, but this is the approach I'm going to use. Okay, the probability of the text will be based on letter combinations, and I'm going to just look at 2 letter combinations. And appearance of real words. Okay, so if we see like a real word, we go, oh, great. Appearance of real words, you know, and better if they are frequent words. Okay, so we're going to look at basically, we're going to figure out the probabilities of these 2-letter combinations. Okay. Anybody know what the most common 2-letter combination in the English language is? It's the combination TH. T followed by H is the most commonly appearing 2-letter combination because we use the word the very frequently. So it shows up the most. The is the most common word, and in English, the combo TH is the most common. Okay. And so what we want to do is we want to figure out basically the probabilities of all 2-letter combos. Okay, and so we're going to do the 26 letters plus space. We will get 27 characters. Ignore everything else. And so now we have 27 by 27 2-letter combos. Okay, and so we're going to start off with AA, followed by AB, followed by AC, to AX, AY, AZ, and then BA, BB, BC, until BZ, CA, okay? And we're going to keep going until we finally reach ZX, ZY, ZZ. Oh, I guess, oh, there should be Z space. I should insert into here. A space, and insert into here, B space, sorry. And then we'll have space A, words that start with A, words that start with B, words that start with Z, and technically I guess we would have a space, but so we could figure out all of these things, okay? So we're going to figure out the probability for each of these things. Each two-letter combo. Okay, the sum across all 27 by 27. I don't know what's 27 times 27. Something. I don't know. 27 times 27. Okay, so the sum across all 729 combos is 1, right? So if we add up all 729 probabilities, we should get 1, okay? TH will be the maximum, the largest value, okay? And then, I don't know, QP will probably have a very low probability. Okay, I don't know, what other combinations will be very low? Like JX, I don't know. Other stuff, right? So just other combinations we'll say like, yeah, can't think of very many words that have those combinations. Okay, so there is some code that was written up. Okay, well, first of all, let me pause here and just say, does all this make sense? Is everybody good here? And let me also give you your second view quiz answer. Second view quiz answer today is the letter E. E as an elephant. E as an elephant. Where did I put my code? So we took a very long English piece of work in English, okay? So I have some code. All right? And what it will do is we take the English text of the novel War and Peace, which is known to be this very long book. I don't know, has anybody read War and Peace? You read it? Okay. Well, it's a very long novel. I have not read it, okay? But we're going to take the English translation. War and Peace, okay? And the code reads every line. Counts and adds a tally for each two-letter combo, okay? So here's, I have this document, and I guess it goes, right? Okay, so I don't know if you can see this, right? So it says, the farther forward and nearer the enemy he went, the more orderly and cheerful were the troops, okay? So it's gonna go through, what this code is gonna go through, and it's gonna say, okay, I see TH, I see HE, I see E space, I see space F, I see FA, I see AR, I see RT, so on and so forth. It's gonna go through every single 2-letter combo, and it's gonna say, all right, I saw TH, we're gonna add it 1, tally to TH. I saw HE, I'm gonna add a tally to HE. I saw E space, I'm gonna add a tally to E space. And it's gonna do this for every single one of these things. And do I actually want to run this? We'll try it, okay? So I'll run it. We read, it's going through the text, and I forget how many lines of text there are. I think 66,000 lines of text in that text document for War and Peace, which was just taken from Project Gutenberg or whatever. I regret starting this. And so it goes and it adds this. All right, and we gotta wait, okay? All right, but here, let me tell you a story while this is going. The result of this 2-letter combination, understanding that certain letter combinations are more common than other combinations, was what allowed you to have a smartphone today, all right? Now, what I mean by that is, I don't know, prior to the iPhone. So the iPhone, I think, was released in 2007, something around there. I don't know how old you guys were. It would have been like 5 or something, okay? I don't know. How old were you in 2007? 7. Okay, you were born in 2000. Okay, so I don't know if you remember, prior to 2007, people had smartphones, but they all had physical keyboards. You had the BlackBerry, okay? And when Obama was elected, he was famously, like, he had the BlackBerry and they had to take it away because it wasn't secure and stuff. So anyway, the reason why was they had tried on-screen keyboards prior to the iPhone, but everybody hated them because the accuracy was terrible, okay? And the problem wasn't that there was a problem with the keyboard. It was just that people were very bad at hitting the exact spot on the screen for each key, and there was no kind of tactile response, right? With a physical keyboard, a tiny little physical keyboard on the BlackBerry, you could actually feel the different keys, and you can be sure you're gonna hit the letter H, you're gonna hit the letter E, and things like that, okay? And Apple, or somebody, I don't know, but Apple used this to power the iPhone. What they realized was certain letter combinations are more likely, and therefore, when somebody types a letter, we can change the size of the keys. So after somebody types the letter T, we're gonna make the key for H, the size of the key for H bigger, and the size of the key for, say, Q smaller, okay? Now, it doesn't show on the screen, but internally, the parts of the screen that are mapped to the letter H actually get bigger and smaller. And you can test this out right now, okay? Take out your phone, start a pretend text to a friend, okay? And what I want you to do is, where's my on-screen keyboard, okay? So look at the space, when you pull up your key, look at the space between G and H, okay? And I want you to type out the word Bing, T-H-I-N-G, but, hold on, don't do it yet. When you type the letter H and when you type the letter G, intentionally hit the space between G and H. So type T and then hit the space between G and H, I-N, hit the same space between G and H. And what you will see is that your phone will, first after the T, it will register that space as an H. After the letter N, it will register that space as a G. Is that happening for everybody here? Okay? And it's not that, again, when you do this, the keys look exactly the same, But the internal mapping of what part of the screen goes to the letter H and what part of the screen goes to the letter G changes as you're typing, because the computers know that after T, H is more likely than G. After the letter N, G is more likely than H, right? And so when you type out T-H-I-N-G, even if you intentionally hit that space in between, it's going to register correctly. And this just happens all the time in the background as you're typing, and we've learned even more about texting, keyboard habits, and stuff like that. And so it just happens seamlessly, and so you, as the user, just perceive that this thing works, and we can get the correct letters. But this stuff is happening magically in the background, okay? All right, so anyway, this has finished. And so I have to install something. I'm trying to get this this thing mapped, right? So, so anyway, Apple recognized this and they implemented it into their keyboard, and then people liked the on-screen keyboard. And now now you can't imagine purchasing a phone with a physical keyboard, right? It just seems, it seems so bizarre, that idea. And that's because, you know, these on-screen keyboards are now very reliable, and we like them. But we like them now because they work, okay, with this thing. Okay, and so this is kind of the resulting picture that we have. Let me show you. So here is I need to shrink this. Okay, well anyway, so what we see is that T followed by H, very dark, very high probability. H followed by E, very high probability, right? If you look at T followed by G, okay, low probability, okay? Whereas if you look at N followed by G, it's a very high probability versus N followed by H, very low probability, okay? And so these kind of these differences are powering your on-screen keyboard so that when you type things, okay, and you're not hitting exactly at the center of your key, it's going to still register probably the correct key most of the time. Okay. So that's pretty cool, right? All right, hang on, how do I do this? So I want to do this, so this is kind of the different letter combinations that we get. So this is from reading War and Peace, which may or may not be reflective of the overall English language, okay? What we see is there are a lot of words that end with E, so E space is very common. We see words that start with A are common, words that start with T are common. So these are space T and things like that. Other things that are common, I-N, A-N, E-N, O-N, those are very common letters. And then A-R, E-R, O-R. So these are all kind of like common word endings, right? So anyway, this is what we have. Okay. And I guess I'll put in the these letter combo probabilities to improve accuracy. Okay. T-H-I-N-G. So tap. Okay. All right, so that's that. Oh, we're gonna run out of time. Okay, so we're gonna use that as one way to evaluate the two-letter combinations. Okay, the probability of the text. All right, and then the other part is we're going to figure out the probabilities of real English words. Okay, so we're gonna say the probability of the text given some particular character mapping. The way we're going to figure this is going to equal to the probability of our two-letter combos plus, basically, we're going to have some constant term times the probability of real English words. Okay? And so this part if we see real words in the text, or I say real words in the deciphered original message, this will increase the probability that, it was the original text, that it was the intended message. Okay? And so what we will need, so for this, we need a quote-unquote lexical database. Okay. And this will be a listing of words and the relative frequency in English. Okay, so I think the word the shows up around 0.0528 of the time, okay? And basically you can go on, I think, Wikipedia, probability of most. Can I help you guys? Common words in English language. Alright, so I think most common words in English. So we have the, be, to, of, and, a, in. And then there is something, let's see. Look up the frequency lists in Wiktionary. They're somewhere. There's different resources. Okay, so there's different ways to kind of calculate this. And so this one was based on TV and movie scripts, right? So it's the idea of like, what is the most commonly used words? It's a little bit strange, right? Because we have written English, and then we have spoken English, things that appear in TV and movie scripts are probably a little bit closer to spoken English. If we look at Project Gutenberg, which is like a bunch of like classic novels and stuff like that, it's going to be a little bit different and things like that. So anyway, I think here they looked at, there's like a count of each of these things. So I guess in TV and movie scripts, the word you and I appear most frequently, and that kind of actually makes sense, right? Because when we're talking about in conversation and stuff. So anyway, I forget which. I think I ended up using this frequency list, which, and we get, oh wait, no. All right, I forget which one of these things I used. All right, well anyway, there's a whole bunch of these things, right? So I think words like the end up being, is the most frequent, and then, you know, in has a probability of something like 0.0196. And if you look up, say, the word friend, it's something around 7 times 10 to the negative 5. And if you look up the word friendship, it's something around 1.7 times 10 to the negative 5, okay? And basically what we're going to do is, if any of these words appear, we'll include its probability. And, you know, if the word doesn't exist, we don't want to put probability 0, but we want to put some very, very small probability in there, because it's always possible that the original user wanted to send like the wrong, like a code, or possibly that they misspelled the word and things like that, and so it might not appear in our list. So we don't want to say 0 probability for any word that doesn't appear in our list, but some very small probability. Okay, I'm sorry, I'm over time. Let me give you your last view quiz answer, which, let me look this up, is the letter A. A as in apple. A as in apple. Okay, so anyway, we'll continue this on Friday. Good luck as you guys study. We'll see you guys on Wednesday for the midterm exam. I'll send out another set of seating assignments and whatnot, and we'll see you guys then. All right.